Okay, let's go ahead and start. Thank you everyone for joining us for the Emerging Market Opportunities for Air to Water Heat Pumps. Today is the second part of the 4-part mini-series. My name is Carly Fletcher. I will be the moderator today. I work at Intertech and I do marketing and events. And then we'll also have Tim Wright, Vice President of Sales, Jim Cusack, Special Projects Manager, and then Jeff Hammond will also be joining us for a little bit, and then John Siegenthaler of Appropriate Designs. And then just to make sure everyone gets the most out of this webinar, I know we will be covering a lot today. Make sure to take as many notes as you can. You can submit questions in your control panel under the questions section, and we will get those answered at the end of the presentation. If they do not get answered, don't worry, we'll reach out to you directly and make sure they do get answered. And then we will also be presenting this presentation and the slides after the webinar. You'll be getting an email, and then you can also check our Intertech YouTube page where it will have it. So I will go ahead and pass it over to you, Tim.
Okay, good morning, everybody. Thank you for taking time to join us again for part 2. We're excited to have Jim Cusack and Jeff Hammond, as Carly said, for a little while, and then obviously our guest of honor, Mr. John Siegenthaler. So super excited to log in, and everybody, it's starting to see the unit count come up, so people are getting signed on. That's awesome. But today we're going to spend time on system design details for air to water heat pumps. Again, that's obviously today. And then next Tuesday, we're going to hit retrofitting air to water heat pumps into existing hydronic systems, which again, super excited about that one from the standpoint of where this system can show up in retrofit or existing home applications or buildings for that matter. And then the fourth and final will be on February the 16th, example systems using the Intertech air to water heat pumps. So all of these are going to be continued lively conversations, phenomenal questions that came in last week. So we're excited to get this going. But John, thank you so much for agreeing to do this and just helping us not only build a nice strong foundation for air to water heat pumps in general, industry perspective, but also to share the intricacies of what Intertech's air to water heat pump, the Advantage system, is able to do. And folks, please keep in mind, as Carly said, these are all being recorded, and we welcome you to come on back to Intertech YouTube channel and then Intertech University. So John, with that, I'm going to let you take it away. And again, keep those questions coming. They were fantastic last week. Thank you, John.
Yeah, thank you, Tim. Good to be with you folks this morning. What we're going to talk about today is, as Tim was talking about, we're going to dive into some of the nuts and bolts. We're going to look at a basic system layout where we're providing space heating, cooling, and domestic hot water. Then we're going to look at buffer tanks, and buffer tanks can be piped up in different configurations. We're going to show you 3 different configurations and talk about the strengths and limitations of those. We're going to talk a little bit about the outdoor details, basically getting this unit up above snow and keeping it away from pollutants or keeping it away from sources of vapor that are just going to load up the coil in cold weather. And then we're going to look at low temperature heat emitter options. One of the critical design concepts with any heat pump, be it a air to water heat pump or let's say a geothermal water to water, going to a hydronic system, is to keep those supply water temperatures as low as practical. The lower we can keep those temperatures, the higher the coefficient of performance on that unit is going to be. We're also going to look at dual fuel options, and by that we mean, for example, in a retrofit, there may already be a boiler present in the system, and when we add the heat pump, how do we tie that boiler in? Or in a new construction application, if somebody wants a backup, there are different ways to pipe that in. We're going to show you some different options on that. We're also going to look at a bit of chilled water piping details. And of course, one of the advantages that the heat pumps have over boilers, they can produce chilled water, so we can do chilled water cooling systems. And it is important when you're doing chilled water that you respect insulation on the pipes, vapor sealing, make sure we don't get condensation forming where we don't want it. And then I'll finish up. I'm going to show you a project I was involved in last year that represents many of these concepts, the low temperature emitters and different types of heat emitters going into the same system and how we can handle that. Okay. Now, last week we left off with a slide like this. And over here on the right, you'll see, I'll start with the outdoor unit, the air to water unit, and then we have a glycol water solution that comes into the indoor unit. And that indoor unit is, think of it as the hub, where we're taking energy from the heat pump and we're sending it out either to a domestic water heater over here on the right, or we're sending it up through a device called a hydraulic separator. We're going to get into that a little bit more in detail later on. But one of the things that that separator is doing is it's providing our air venting for it. So we're taking the dissolved air bubbles that are in that water initially and getting them out of solution. So we'd like that hydronic system to have the minimal amount of dissolved air content. And then to the left of the separator, you'll see state-of-the-art distribution system. This is a variable speed pressure regulated circulator. I'll show you several products that you can use today for that. And then farther over here, these are zone valves. And I'm showing them going out, in this case, to some radiant panel manifold stations, or perhaps one of them, or more than one of them, could go to a chill water air handler. And that air handler could also be used in heating mode. So this part of the system, it's almost limitless what you can create using hydronics technology. The important thing is keep the water temperatures low for good performance on that heat pump. So let's talk about buffer tanks, okay? The idea of a buffer tank, anytime you have, and I'm going to make reference here to a heat source that has a fixed heat output capacity, and the Enertech unit does have variable capacity, but when you have a heat source that has a fixed capacity, and I'll just divert from a heat pump. Let's say we're talking about a boiler. It really doesn't matter what that heat source is. It's a box that produces heat at so many BTUs per hour, and we're coupling that to a distribution system that might be highly zoned. We might have each room in a building as a separate zone. Or we may have some small rooms that have small emitters that only need maybe 1,500, 2,000 BTUs per hour. So imagine what happens when we take a heat source that produces 50,000 BTUs per hour and we try to connect it to a heat emitter that only releases 2,000 BTUs per hour. We have a huge surplus of heat production. And we've got to do something with that heat. That's basically where the buffer tank comes in. It's a temporary storage device for that heat. Now, when it comes to sizing a buffer tank, there's a couple things that we want to do here. What is the minimum runtime that we want that heat source to operate with where it is not short cycling? And there's no formal definition of a short cycle. If you asked people involved in the trade, if their heat source turns on and runs for 1 minute and then shut off, is that a short cycle? Most of them would say yes, and I certainly would agree. 5 minutes, probably a few less would say that's a short cycle. I like 10 minutes as a reasonable number. If we're turning on a compressor in the case of a heat pump, or if we're turning on a burner in the case of a boiler, that we would like to see that run for a minimum of 10 minutes, just so we aren't accumulating literally tens of thousands of on-off cycles over the course of the heating season. The other thing we have to look at is how much of a temperature change will the buffer tank undergo while that heat source is on. The smaller the temperature change, the bigger the buffer tank has got to be. So you can put this together mathematically. It's actually a pretty simple calculation. If we want to calculate, I'll say the minimum volume of a buffer tank, V, all right? Well, T here, this would be the desired duration and heat source on cycle. Let's say we're going to make that 10 minutes, okay? We have to know the heat output rate in BTUs per hour of our heat source. And I should mention, again, this this formula is independent of actually what the fuel is or what the heat source is. It's just a rate of heat production from some heat source. And from that, we could subtract what would be the minimum load that could be running at the same time. Now, that can be zero. You can turn a heat source on and simply charge a buffer tank up with heat without having to have a call for heat from the distribution system. That is one control option, okay? And then we divide by a factor of 500 that's related to the heat capacity of water. And we're also dividing by how much of a temperature change that buffer tank is going to undergo from when we turn the heat source on to when we turn it off. And I'll give you an example here. Let's say a designer has a hydronic heat pump and it's rated at 48,000 BTUs per hour. So it's a 4-ton heat pump, and we want it to run for 10 minutes. And let's say that during that time, we're going to have a towel warmer radiator releasing 2,000 BTUs per hour. Okay, the heat pump responds to the buffer tank temperature. It turns on when the buffer tank drops to 100 Fahrenheit, and then it turns off when the buffer tank gets up to 120. So there's our delta T between heat pump on and heat pump off of 20 degrees. So really, it's just a matter of putting those numbers into this formula, all right? And it calculates out to be 46 gallons, okay? Now, again, that's a theoretical estimate for the volume. You know, if you put a 50-gallon tank in, that'd be fine. If you put a 40-gallon tank in, that it's probably going to, the run time is going to go down a little bit. So I put down here, larger buffer tanks will provide a longer heat source on cycle. So that's ultimately less wear and tear on a compressor, or in the case of a gas boiler, it would be less wear and tear on that ignition system, okay? But obviously a bigger tank costs more money. So it is a trade-off, and you know, different people may have different opinions on it, but I'd like to size buffer tanks so that if we're running that heat source at full capacity, we get a minimum of a 10-minute run cycle on there. Now, when we pipe the buffer tank, there's different ways to do it, all right? And what this says here, a buffer tank should be installed between the heat pump and the distribution system whenever the smallest zone load is less than the minimum heat pump modulation capacity. In theory, if we had any heat source, a heat pump or a boiler that could modulate from 100% right down to literally zero, we would not need a buffer tank, because we could always adjust the heat output of that heat source to match what our distribution requirement is. But we have minimums on the heat pumps. We can talk about that later on. But let's say, again, we had a nominal 4-ton heat pump, and we have one of these, what I call micro loads. It could be a small towel warmer or a panel radiator in a room. It's very small heat requirement relative to what even the minimum modulation of the heat pump is, okay? Now, the classic way to pipe a buffer tank is what we call a 4-pipe configuration. And this could be a heat pump, this could be a boiler. And you see we've got a circuit with a circulator in it that basically puts heat into the buffer tank. And then on the other side of the tank, we've got a circuit that takes heat out, all right? And some of the characteristics of that are beneficial and some are not as beneficial. We're going to talk about that in a little bit more detail. I want to show you the other two configurations, and then we'll go back and kind of take each one of them apart. This is a relatively new configuration to most people in North America. It's called a 2-pipe configuration. And I'll tell you a quick story. When I first saw this, we were dealing with pellet-fired boilers, and I was looking at heating schematics coming out of Europe and looking at that and saying, well, you know, I see how they did everything, but they goofed up on their piping on the buffer tank. I thought this was incorrect. And I started studying it more and thinking about it and reading more about it. And there are some advantages to this. One of the advantages is what's called direct to load transfer. If the heat pump and the load are operating at the same time, with this configuration, it is possible to send heat directly to the load without first having to warm up the mass of the buffer tank. And that can be an advantage coming out of a setback condition, for example. All right. The other thing that happens with a 2-pipe buffer tank is there's actually, when the load and the heat pump are operating simultaneously, the only flow that's actually going through the tank is the difference in flow rate between the heat source flow rate and the load flow rate. So let's say the heat pump was operating at 12 gallons per minute and the load was taking 8 gallons per minute. The difference would be 4, and that's what's going into the buffer tank. Now, why does that matter? The slower the flow going into the, I'll say the lower the volumetric flow rate going into the buffer tank, the less disturbance of temperature stratification in the tank. And temperature stratification is good. I've had people say, no, you want to fully mix that tank. That really, from a thermodynamic standpoint, is not ideal. It's not necessarily going to destroy the performance of the system, but from a pure thermodynamic standpoint, stratification of temperature in a buffer tank is actually beneficial. So we've talked about over here on the left a 4-pipe configuration, and then I'm showing you a 2-pipe configuration. So what do you get when you average 4 and 2? Well, you get 3. And here's a 3-pipe configuration. And I really like this with a heat pump. What this does is it gives you direct to load on the supply side. So we still have that ability to take heat directly from the heat pump and take it right out to the load without first going through the buffer tank. But we're always assured that we're engaging the thermal mass of the tank, because all our return flow has to go through, in this case, the lower portion of the tank. And this can actually help with stratification as well, and it can help with keeping minimum water temperatures going back to that heat pump. And that's going to help ultimately the COP of the heat pump, to keep the water as cool as possible. If we fully mix these tanks, we're taking some of the warmer water at the top, and we're actually increasing the temperature near the bottom of the tank by blending these two together. And that's going to bring that water temperature up perhaps a few degrees Fahrenheit going to the heat pump. And from what we talked about last week, that is going to bring down both the coefficient of performance, and it's also going to slightly bring down the heating capacity. So let's look at a 4-pipe in more detail. All the energy that leaves the heat pump must pass through the buffer tank to reach the load. There's no way around that, okay? If the buffer tank is cool, let's say the heat pump's been off for some reason, for several hours or perhaps 2 or 3 days, to get heat out to the load, we're going to have to first warm some of the mass within that tank. Now, when it's piped like this, it's true that the warmer water will tend to stay near the top of the tank and go across here, but there's always going to be some mixing occurring here, okay? And that is going to represent a delay in getting the temperature to the distribution system the same as the temperature coming out of the heat pump, okay? Now, one of the nice things that a 4-pipe configuration does, it provides what's called hydraulic separation. And if you're new to hydronics, this is a really important concept. Anytime we have 2 or more simultaneously operating circulators in a system, the ideal scenario is we don't want those circulators interfering with each other. And imagine one is a larger circulator and one is a smaller circulator. You know, if you run them both at the same time and you let them interfere with each other, what's going to happen is, basically think of circulators as bullies on a playground. The big circulator is the big bully, and the big circulator is going to dominate the pressure dynamics in the system, and that can cause flow problems for the small circulator. And we've seen this happen over the years. Again, this is really independent of what the heat source is, but when you're designing hydronic systems around any heat source, it is always beneficial to have hydraulic separation between the circulators. And the ultimate concept of hydraulic separation is each circulator thinks it's the only circulator in the system. And when it turns on, it provides a certain flow rate and a certain differential pressure. And that flow and differential pressure are not affected if another circulator happens to turn on or off in the system. That's the ideal scenario. And piping a buffer tank like this is one way to achieve good hydraulic separation between the heat pump circulator and the circulator for the distribution system. Again, all the thermal mass of the tank is fully engaged here, okay? In many cases, that's a beneficial effect. In some cases, when the tank is cold and we're trying to get energy directly to the load, it tends to work against us. Now, another important detail, anytime you have a warm thermal storage tank, and you have a piping circuit that goes from the upper portion of that tank to the lower portion, you really want to make sure you put a check valve in that circuit, because let's say we take this check valve away. What will happen is the water, the warm water that's out in this pipe, is going to give up heat. And as it gives up heat, it becomes denser. And as it becomes denser, it's slightly heavier. And that's going to start to go backwards through this circuit if there's nothing preventing that. And ultimately, what you will get is called reverse thermosiphon. And over time, this will tend to dissipate heat from the tank. All right. This was a huge problem with solar thermal collectors going back 40 years ago. I don't think anybody really realized how much of a factor that was going to be. And it becomes a factor really in any system where you have a thermal storage tank and a piping loop that is not blocked. And remember, a circulator without a check valve in it does not block flow. Flow can go backwards through a circulator when it's off. So I'm showing here a swing check valve, and also over here, this circulator, just to show something different. Many of the small circulators today are supplied with a small check valve insert that has a spring on it, and that spring will open at roughly about half a PSI. So that's sufficient to block that. In this case, it would be forward thermal siphoning when the circulator is off. Okay, so those again are a couple important details for any hydronic system with a buffer tank. Now, in a two-pipe configuration, I mentioned this direct-to-load concept, all right? And what the difference is, you can see, instead of taking the load circuit off over here on the right, we're taking the load off just upstream of the buffer tank. So we can intercept this water coming up through here and send it out through there. So we do have the advantage that if the tank was cool, we could get warmer water to the load faster with this configuration. I also mentioned that when the load and the heat pump are operating simultaneously, the only flow that is going through the buffer tank is the difference. Now, that can be a problem. Okay, I'll give you a scenario. Let's say the heat pump is operating at 12 gallons per minute, and let's say the load is taking 12 gallons per minute. All right, so what's happening is all this flow is going up to the load, it's coming back, and it's going back to the heat pump. So there's our circuit right there. And under those conditions, you have zero flow going through the buffer tank. Well, if those conditions persist for a long time, there's kind of no point in having the buffer tank. It's like having a battery and you're not charging the battery at all. So I want to drive home the point, if you're doing a two-pipe buffer tank, it is important that you're controlling the heat pump based on a temperature of the water in the buffer tank. We're not turning the heat pump on and off based on a thermostat that's out in the heated space. We're turning the heat pump on and off based on some kind of a temperature condition that we're trying to maintain in the buffer tank. It could be a set point with a differential. For example, it could be turn the heat pump on when the buffer tank drops to 95 degrees and then run it until the buffer tank gets up to 105. That's a 10-degree differential. That could be the logic. Or it could be an outdoor reset controller. Outdoor reset control is basically going to change the temperature, the on and off temperature for the heat pump in response to how cold it is outside. So on a mild day, we might let the buffer tank temperature go down to, let's say, 80 degrees, and then turn the heat pump on and run the tank temperature up to maybe 90 degrees. And the benefit of that, again, is the lower we can keep the water temperature back to the heat pump, the higher the COP is going to be. So there are different control algorithms, I'll call them, but because of how this tank is piped this way, it's important that we control the heat pump based on that tank temperature. The other detail I want to stress is over here. One of the things that can happen, and we've seen this happen, is we'd like to think that when we send hot water up to the load and it cools down, it comes back down, and let's say the heat pump is off, okay? Heat pump's off. We'd like to think that the water has the intelligence to know when it gets to this T that it's supposed to go this way through the buffer tank and drive warm water back up through the load. It turns out water doesn't have much intelligence, all right? Or I could say maybe the water's outsmarting us if we don't put this certain detail in there. What can happen is some of that water is going to go this way without this device in place, okay? And some of you may be thinking, well, I'll just use a circulator with one of those built-in check valves. Well, those built-in check valves can only hold back at most about half a PSI. And in some cases, if you have high flow rates here, you might actually build up more than half a PSI differential between this T and this T, and that is going to overpower the spring in that check valve, and it's going to send some of that water up through the heat pump. Now, that doesn't hurt the heat pump. It doesn't hurt a boiler. But what it does do is it just unnecessarily cools some of that water. You're sending it through piping and through a heat exchanger in a heat pump. And even though that heat exchanger in the heat pump is insulated, that reduces some of that loss, you're going to have some losses there. And so that water is going to cool off a little bit, and then it's going to blend with the tank water, and it's actually going to bring that supply temperature down a little bit. And I will stress, with the heat pump, it's not as much of a factor as it is with a boiler, because a boiler does not have that insulated heat exchanger in it. And you can lose several degrees as that water goes up through there. But one of the ways that we've found works well to prevent that is to put in what's called a differential pressure valve. And these are available from several manufacturers, and set the spring in there. You just adjust the knob for a forward opening pressure of anywhere from 1 to 1.5 PSI. And that's a strong enough spring pressure to prevent that flow from going back this way when the heat pump is off, all right? And it also replaces the need for the check valve. So you can think of it in effect as an adjustable check valve, or adjustable spring check valve, to get a little bit more differential pressure. And finally, I'll leave you with a detail. If you do this configuration, this header should be as short as possible and keep the pipe size as big as possible. We're trying to minimize any pressure drop through the tank between this T and this T. And if we do that, this configuration will still give us good hydraulic separation. Okay? So don't take this T and put them 50 feet away from the buffer tank. That's going to build up more differential pressure in this portion of the circuit, and we're starting to lose this beneficial effect called hydraulic separation. So 4-pipe, 2-pipe, now let's average them out. Let's go to a 3-pipe. We're still getting our direct to load transfer, so we're retaining that benefit. All the return flow has to come back through the tank, through the lower portion of the tank. So we are fully engaging thermal mass. There's always going to be some flow going through the tank, okay? Which, again, I gave you that scenario with the 2-pipe buffer. I would still recommend controlling the heat pump based on the tank temperature rather than the thermostats. But I will say, with this particular option, because we always have flow coming back through the tank, that is not an absolute essential requirement as it would be with the 2-pipe. So I tend to like this approach with heat pumps, especially the direct to load transfer, and keeping this cooler water down here at the bottom going back to the heat pump, okay? And again, make sure we get that check valve in here so we don't get a reverse thermosiphon flow going backwards and dissipating heat from that tank. Now, Enertech does have a buffer tank for sale, and it's a nice tank. I've actually used this tank in a project with water-to-water geothermal, and it is a polypropylene tank. This pressure vessel right here is made out of polypropylene, and it is wrapped with a fiberglass layer, and that provides the pressure shell, if you will, for that polypropylene. And then the whole thing is foamed, and there's a polypropylene jacket on the outside. So literally, it's a non-metallic tank. So it does not, there's no corrosion concern with it. And it's a very well insulated tank. If you're dealing with chilled water, I found that the tank, it really is a well-built tank. I'm showing the indoor unit of the air-to-water heat pump piped up to the tank. Here's the check valve, so we don't get that reverse flow back during the time when the heat pump is off. But I'm taking the outlet to the load off the very top of the tank. You know, it's conceivable you could take it off here, but the reason that I'd like to see it up at the top is you're getting the very hottest water in the tank. And there is some slight temperature difference between this level in the tank and the very top. Remember, the hottest water in the tank is going to be the lowest density. It's going to be up at the very top. Now, one of the things that is important with this tank is a vacuum breaker, and that actually is supplied with the tank. The reason a vacuum breaker is there, if you have a system and you have hot water in there, and the tank is allowed to cool down, or the tank goes into a chilled water cooling mode, that water is going to shrink in the entire system. And the expansion tank, the diaphragm in the expansion tank may bottom out against the shell of the tank. And at that point, that water, remember, water is an incompressible fluid. That water is actually going to be pulling inward on that polypropylene liner. And to prevent any damage in the tank, that vacuum breaker needs to be installed. It's a very simple little component. I'm just showing it teed in up here at the top. And then going off to the right, we've got a microbubble air separator in there and our circulator, and we go off to whatever our load is, okay? So again, here's some facts about how this is going to work. The heat pump does have a variable speed compressor. As we come up to a temperature set point, that compressor is going to slow down. So again, I would recommend a tank like this, especially if you're going to use it for chilled water service. Now, that brings us up to our first poll question. I'll read the question, and then Carly is going to monitor the responses on that. We've talked about these three different types of buffer tanks. Which buffer tank piping configuration do you have experience with? And check all of them that apply to what your experience has been. So I'm going to pause there while that poll is running. And here we go. Starting to get results in. And yeah, I'm watching the results come in. It looks like the 4-pipe is winning, and that is not surprising. But I am pleased to see we have some decent numbers for both 3-pipe and 2-pipe.
Okay, I'm gonna go ahead and close it.
Yep, okay, so here's what we got, folks. We got 75% of the respondents have experience with a 4-pipe buffer tank, and 23% have experience with a 3-pipe configuration, and 40% experience with a 2-pipe. And I am surprised. I thought that would probably be something like 90% with the 4-pipe and maybe 5% each on a 3-pipe and a 2-pipe. So again, they're different options. They have strengths, they have limitations. Of all three, I tend to like the 3-pipe the best, but any of those configurations can work with the detailing we've talked about. Okay, so let's go on here. Outdoor details. Now here's several different types of air-to-water units. Most of these are monoblock. A couple of them are split systems. And the important thing here is, remember that we're going to use this in a winter. These are suitable for cold winter climates where we get a lot of snow. And we want to make sure that that heat pump is elevated up off the ground. And I'm going to suggest a minimum of a foot. We want to get it up not only away from snow, but by getting that unit up, we get it away from grass clippings, leaves, bugs, you know, the dog going out there and thinking it's a hydrant, that type of thing. And you can see these are different ways of supporting the heat pump. This is actually one where they put a couple units in and they actually built a little alcove. It's up on some treated lumber here, and it's got an overhang over it to protect it from the rain. This is a low capacity unit, a split system, and you can see it's up on wall brackets. There are brackets that are out there that have the strength to do that. Obviously, you want to make sure that that bracket system, if you're going to do this, is rated to hold the weight of whatever unit you're going to put on it. Here's another common approach. This is an adjustable steel stand where you can adjust the height of those legs. It is important, again, in my opinion, what you don't see here under this crushed stone, there's two pressure treated 2x8s, and that stand is fastened down to them, and they're actually down in the ground 3 or 4 inches. It's important to make sure these units are fastened down. If you get a strong wind, and you know, I don't mean an everyday breeze, but imagine a 40 or 50 mile per hour gusty wind, these units can rock around. So you want to make sure that you've got that secured against any kind of wind buffering. And then just to show you what happens with one of these units when it goes into a defrost, if you look over here on the left, lower left, if you look carefully, you can see the water pouring out of the bottom of that unit. If that unit is just sitting on a concrete slab, what can and has happened is that water will tend to accumulate in the bottom of that unit. It won't fully drain away, or it'll run out of the unit and form an ice dam. Literally, it'll build almost a dam around the back side of that unit, and that's going to further hold condensate against that coil. And I have known of coils that have failed because of the expansion and contraction of ice when that condensate water is not properly drained away. So make sure that that unit can drain that condensate. Again, the Enertech unit does have a tube, and it does have a heater in it so that it doesn't form ice within the unit, but make sure that you provide a provision for that condensate to go away. And you can see when this unit, this is a nominal 4-ton unit, when that goes through a defrost, it probably drops, I'm going to say 2 pints at least of water. Okay, so keep it up off the ground, make sure that condensate can drain away from the unit. This is the stand that Enertech has available for the heat pump. It's a heavier gauge aluminum stand. You can see it's on a concrete base there. You know, for an area with moderate snowfall, that would be adequate. If you live in the Tug Hill area of upstate New York, they get snow measured by the foot up there. So it's not uncommon to see 3 or 4 feet of snow on the ground. And in places like that, you want to get that unit up even higher. Okay. Now, what are other factors? Well, basically, we don't want sources of moisture around the outdoor unit. And the reason for that is if we have, for example, a dryer vent, or if we had a vent from perhaps a gas-fired boiler in the house, that produces a lot of water vapor coming out the vent. That coil is cold. It's definitely colder than the outside air temperature. So imagine it's 10 degrees out. That coil is going to be at a sub-zero temperature, and any source of vapor around it is going to freeze against that coil and just force the unit into more defrost. We want to keep it away from exhausts in general, any kind of an exhaust. If you have a wood shop and you're producing sawdust or some other type of dust, we want to keep it away from there. We want to keep it away from where vehicles would be running, again, with the water vapor coming out of the exhaust pipe. Okay. Don't put the unit directly under an overhang unless there's a gutter. And if you look really carefully at this photo in the upper right here, you can see there is a gutter across the top of that unit. I can imagine a situation where we have a 2-story house with a steep metal roof, and the snow might slide off of that metal roof and come down 2 stories and land directly on top of that heat pump. Obviously, that's not a good idea. So, when you're looking at a potential location for that heat pump, make sure you look at things like roof runoff or snowfalls or drifting snow. We want to keep it away from animals. We don't need the dog scratching on the side of the coil there, so to speak. Obviously, any kind of flooding, any kind of debris accumulation. Most of this is common sense, but we put this down here to keep you thinking about where to put that unit. And I put down here at the bottom, all other things being equal, if you can put the unit on the south side of a building, you are going to benefit from what we call a slight microclimate effect. The air is going to get a little bit warmer on the south side of that building when the sun is out during the day, and that's going to give you some benefit in terms of heating performance. Okay. Now, we want to keep the system, certainly the indoor portion of the system, as quiet as possible. Anytime you have a compressor, inevitably you get some slight vibration, okay? And I'm showing here a detail. This is an air-to-water heat pump with a couple pieces of reinforced hose. This hose is available from several manufacturers. This happens to be by a company called Chamflex. And what that is I believe it's an EPDM inner hose with a stainless steel braided liner on it. And one end has a swivel union. The other end, in this case, it's a 1-inch nominal pipe size that just has an FPT connector on it. And you'll see the pipes are coming out through sleeves. I'll show you a close-up of this in a minute. But I like to see a slight offset. We don't want to go straight out because that doesn't really give us, it doesn't really attenuate the vibrations as good as having a slight offset with the connections. This is another approach. This is a corrugated stainless steel tubing. And you can see, again, it's got unions to fasten to the heat pump or to stub outs coming out of the heat pump, and then some flexible path going back through the piping inside. And again, the idea of the flexible path is to attenuate vibration, and also if there is any buffering from the wind, any slight movement out there, this takes the strain off the piping. So we aren't directly putting mechanical strain on the piping connections on the unit. And of course, you see the disconnects that are required by code out here. Okay. Now, this is just a close-up. This is how we've done it on a project. There are other approaches that would be, as good as this. We take first of all, we take a 1/4-inch pilot drill, 12 inches long, and we drill a straight hole right through the wall. Obviously, you want to make sure where you're going through, you're not drilling into some piping or something else on the other side of that wall. So assuming you've got a clear path, you send the pilot drill through, you've got a straight line, and then take a hole saw and cut a hole through there. In this case, this is 2-inch Schedule 40 PVC pipe, just some DWV piping. And it's got some wrappings of electrical tape just to make a really tight friction seal with the building. The reason we're running that sleeve through the wall, remember in the summer, this can be chilled water. What we don't want to have happen is we don't want condensation to form within the wall cavity on the piping and have that condensate just create mildew or other deterioration inside the wall cavity. Now, the final step here was to spray it with an expandable foam. And that foam expands, it sets up, and then you could just take a hacksaw blade and just neatly trim around that. And then, of course, you want to insulate that piping. This insulation doesn't show it yet, but that outside elastomeric foam insulation should be wrapped with a UV resistant tape so it doesn't deteriorate over time. Okay. Another approach is to run a plastic sleeve, a PVC sleeve through, and then use what's called a Fernco connector, which is it's a flexible rubber connector. It has a hose clamp, a stainless steel hose clamp on each end. You can get those that make a size transition. So if you run a 2-inch sleeve through and you want to come down to a 1-inch or some combination of sizes, they do make those different sizes available. That's another approach. The basic idea is you want to get the piping through the wall. You don't want condensation potential within the wall cavity. And obviously you want to seal it up so you don't have bugs and air and so forth coming through there. okay? Now, let's look at the heat emitters, okay? Again, I think we've probably answered this question multiple times, but I'm going to emphasize it again. We want low water temperatures to keep that heat pump operating at its peak capacity. And I'm going to suggest, and this is not an ASHRAE standard, it's not a code requirement that I'm aware of, but it's a guideline that I've used for many years when we design hydronic systems. And this is across the board now, regardless of what the heat source is. We like to design hydronic heating systems so that at design load conditions, we don't need a water temperature over 120 degrees Fahrenheit, okay? Even lower if possible, and certainly with some radiant panels that we're going to look at, we can get that down another 20 degrees. The reason for this is, certainly with a heat pump, we want good COPs, but think about future-proofing your system. Today, I can legally design a hydronic system for 180, even 200 degree Fahrenheit water temperature. But going forward, 5 years from now, 10 years from now, if somebody wants to take that boiler that's producing that 180 degree water, take it out and put a heat pump in, they're going to have to do an extensive rework on that distribution system. And we're going to talk about some of those things next week. How can you modify an existing system to bring the water temperature down? But when you have a blank slate, you have the opportunity to build a system that's going to last for decades. Keep that in mind. That hydronic distribution system is easily going to outlast its first heat source, maybe even its second or third heat source. It's going to be there for several decades. And why design something today that is going to require extensive modification in 5 or 10 years? Even though, yes, it does cost more money, we need larger heat emitters to bring that water temperature down. In the long term, it's money well spent. Okay, so one of the things obviously you want to think about too, if you're dealing with floor heating, one of the downsides or potential downsides of floor heating is you design the system, let's say for a tile floor, and somebody says, oh, I don't like the tile anymore. I want to put down a nice thick Berber carpet and a 1/2-inch urethane pad on there. Well, that is going to destroy the performance of that floor heating system. So that is one of the Achilles heels, I guess I'd describe it as, for floor heating. So, you've got to ask questions of your clients to make sure that as you design this system, you're not inadvertently designing for something that's going to have a problem later on, okay? Obviously, we want our systems to be as quiet as possible. We don't want drafts, okay? We want to be careful if you're operating any kind of fan coil or air handler at low heating temperatures. I'd suggest nothing less than 100 degrees Fahrenheit. And even at that water temperature, introduce that air very carefully into that space so that it doesn't directly blow on, where somebody is sitting. And some of you could probably relate to this. If you've ever been in a hotel with a PTAC unit through the wall, and they set the desk up right next to the PTAC unit, and literally you're sitting there with that air just blasting across. You can't even keep the papers on the desk. So I laugh about that, but it's kind of a really a bad idea from a comfort standpoint. Now, just some basic concepts. The heat output of any emitter is always going to go down with water temperature. There's no way around it. That's the fundamentals of heat transfer. But there's always some output as long as that supply water temperature is above the room temperature. I put that one in there because I've had actually a couple people over the years say, well, John, don't you know that fin tube baseboard stops working below 140 degrees Fahrenheit water temperature? No, it doesn't. The rating table in the literature doesn't go lower than 140, but as long as there's a temperature difference between the water in the tube and the room air, there's going to be some heat transfer, okay? And then kind of the fundamental trade-off. The more surface area your distribution system has, the lower the water temperature can be. And you can think of that sort of like a seesaw. On one side, you've got the surface area of all the heat emitters. On the other side, you've got supply water temperature. When one side goes up, the other side goes down. So fundamentally, what we're trying to do is create distribution systems that have a lot of surface area, okay? And I put down here just as a guideline, this is kind of a wide range of water temperature and what are some of the traditional ranges that these different heat emitter systems have been applied at. And I'll start with the really high temperature stuff. And actually there was a day when I actually would extend that graph out here to about 230 degrees. There was a day when that was actually advocated. Run your hydronic systems from a boiler with pressurized water, of course, at 230 degrees. And not only is that a safety issue, if you lose the pressure, you have instant steam flash. That was done strictly in the days when houses literally had no insulation in the envelope, and they were trying to keep the size of the heat emitters as low as possible. Those days are gone. In fact, I would tell you most of this range, from a practical looking forward standpoint, is not really where modern hydronics is. Modern hydronics is over here, okay? So, you know, we're looking at a range like this, and there's a lot of application here. I've got down ceiling heating, wall heating, several types of floor heating here. One of the ideals is a bare slab. And when I say bare slab, it could be painted, it could be stained. If you've seen some of the stained concrete slabs, they're absolutely beautiful. So minimizing that surface R value is important. Now, when we put a floor covering of some sort, it could be a thin engineered wood plank, it could be ceramic tile. You can see we are forcing that water temperature up. How high does it go? It depends on the R value of that covering. So we're always looking to try to minimize any R value of any floor covering we're putting on there. There are some systems that use aluminum plates above the floor and below the floor. They are going to require some higher temperatures. It is possible to keep them in that 120 range. The way you're going to do that is with close tube spacing, plenty of aluminum plates, and minimal resistance in the floor covering. And then I'm going to show you a couple examples today of ceiling and wall heating as well. All right. So let's start with the slab on grade. All right, a slab on grade. Here's a detail we've used for years where we have good underside insulation. My suggestion to you is that should be nothing less than 2 inches of extruded polystyrene. That would give you about an R10.8. And, you know, I've had people say, well, you know, maybe I can get away with 1 inch, or I could put down a bubble foil product. And I'm going to ask you this question and let you ponder this. If you put down insufficient insulation, how hard is it to retrofit the right insulation under that slab? And I hope a few of you are chuckling, realizing it's virtually impossible. You got one shot in the life of the building to do that under slab insulation right. And again, energy prices are going to go up. So it's a lifetime decision, just like the footings, the foundation. And I would suggest nothing less than 2 inches of extruded polystyrene. Make sure you insulate the edge here. This can be a very high heat loss. There are different details depending on how this wall is constructed. General idea is we want a thermal break here between the slab and the edge. And the other thing you'll see, the tubing has been lifted within the thickness of the slab. In fact, you can see that happening right here. One of the contractors has a lift hook, and what he's trying to do is get that tube and that mesh at approximately half the slab thickness. It doesn't have to be exact, but don't leave the tubing and that welded wire fabric laying on top of that foam. Structurally, the welded wire fabric is doing virtually nothing for you. And from a thermal standpoint, it does require higher water temperatures. We've done a fair amount of research in that area. And I can tell you, even at 15 BTUs per hour per square foot, that's about a 7-degree increase in water temperature if you leave the tube at the bottom of the slab versus the middle of the slab. That's going to penalize, to some extent, performance of any heat pump, whether it's air to water or geothermal water to water. So again, here's some layouts. You can see the contractor's done a nice job. They've started with a tubing layout plan, They put arrows to make sure they get the flow directions when they connect back to the manifold correct. And here's some masons laying it down. Again, the guy in the orange shirt here, he's got the lifting hook and he's pulling that tubing up. Again, you can see some details here, some sleeving where there's going to be control joints and so forth. So there's several resources out there. If you're new to radiant panel heating, you know, I don't want to spend a lot of time into the details, but for example, there's references where you can look at, if I put the tubing 12 inches on center and I have a finished floor resistance of 1, how much heat output will I get depending on what the difference is between the water temperature in that circuit, I should say the average water temperature in the circuit, and the room air. So this is a graph. I use this graph a lot. It allows you to get a quick estimate of output in BTUs per hour per square foot versus what I call the driving delta T. And the driving delta T is just the difference between the average water temperature in the circuit and the room air temperature. The higher that is, the higher the heat transfer rate. And then these different lines, RFF just stands for finished floor resistance. If it's a bare slab, RFF equals 0. If you're putting a ceramic tile over it, probably somewhere is around 1. If you're putting a commercial carpet and you're gluing it to the slab without any kind of pad under it, you're probably going to be about 1.5 to possibly 2. And you'll see that makes quite a difference in terms of the water temperature that you will need above the room air temperature for a certain rate of heat output. And the other thing you can see here, these lines are plotted for both 6-inch tube spacing and 12-inch tube spacing. The closer you bring the tubing, the better the heat exchanger that floor is. So trade-offs there. But again, this is a nice low temperature option. I see a lot of great potential applications with slab on grade buildings and air to water heat pumps. Now, this is one that is definitely lesser known, but this system is actually working with a geothermal water to water, so it would certainly be applicable to air to water. Radiant ceiling heating. And what's going on here, you can see there's a layer of OSB, oriented strand board, that's been fastened up to the ceiling. And then there's 3/4 inch thick foil face foam strips that have been glued with contact adhesive up to that. It's a little hard to see them here, but there are 5-inch wide aluminum plates that fit. Actually, you can see it in the cross section down here. These blue rectangles are the foam insulation. And then if you look carefully, you'll see a red line right here. This is a heat transfer plate, and that's designed to pull that heat away from the tube, spread it out across that surface. The tube snaps into it, and that's what this fellow is actually bending this tubing. This is 1/2-inch PEX aluminum PEX tubing. And then it's what he's doing right down here, he's using a wooden float to just press that tubing up into those plates. And there's no need for any glue to hold it there. Those plates are shaped so that they do capture the tube when you push it up in there. So when it's all done, at least when the tubing's all installed, all the tubing's up here. Here's where he's brought several circuits together, brought them over to an interior partition, and then drilled down through there. And the manifold is actually down in the basement. The manifold does not have to be above the circuits. It's possible to purge the air out of that quite easily, actually, with the manifold being lower than the circuits. And of course, the final step is going to be install drywall over all this. And of course, when the drywall goes up, you don't want to shoot the screws up into the tubing. So typically, you're going to snap some lines and shoot the screws in halfway between the different rows of tubing. 2.5-inch screws work really good, and then just finish it off. So here's a ceiling in a room. This is with an attic truss. And I can tell you, this room is 14 feet wide, and the ceiling is only 6 feet wide. And that ceiling can easily heat that room. And down here is an infrared thermal image of that ceiling. The red strips that you're looking at here show how that heat is being spread out by those aluminum plates. And you can actually see the water is actually flowing from left to right here because these plates haven't warmed up quite as much over here. But this is really good. This shows you it is critically important to have those aluminum plates in there. Literally, that will triple the output compared to just putting the tubes up without any type of heat transfer plates involved. And then if you're looking at a system like this, and by the way, this tubing is all 8 inches on center. The output of that particular system would be this. It'd be the average water temperature in the circuit minus the room temperature times 0.71. And let's say the water temperature, the average was 110, the room's at 70, so we've got a 40-degree differential here. 40 times 0.7, we're getting about 28 BTUs per hour per square foot with a relatively low water temperature. And of course, we could go even lower if our heat load in the space allows us to. So this is definitely a heat emitter system that could be well suited to work with the air-to-water heat pump, as well as a geothermal water-to-water. Now, if you take that same system and just turn it on its side, you get a radiant wall. It's literally the identical construction. It's just on a vertical plane versus the ceiling plane. And you can see here's the fellow putting the drywall screws in. You can actually see that the screws are going in halfway between the tubes, so that the screws don't even go through the aluminum plate. They basically just go through the drywall, the foam, and then they draw up tight against that 7/16 oriented strand board that is behind the foam. Here's a thermal image of that wall when it's operating, and here's what it looks like when it's all finished. I mean, the wall visually is, you have no idea that it's a heated surface. But the red here again is indicating that those plates are doing a good job spreading that heat out. And you might be wondering, what's this? Well, it's a wall around a stairwell. And this wall here and this wall here have that same system installed. So you can be very creative with these radiant walls. You don't necessarily have to heat the entire building with radiant walls, but sometimes there are surfaces that are going to remain exposed. In other words, we don't have a sofa, for example, that pushes right up tight against that wall. And that's an ideal surface to create a radiant panel. Again, this is running at relatively low surface temperatures. You can see in the thermal image, the highest temperature here is only 93 degrees Fahrenheit. So this wall feels just slightly warm to the touch, but there's enough surface area there to heat that entire space. So floors, walls, and ceilings can all be done with radiant panels and all be done with low water temperatures that really allow that heat pump to perform well. Again, the construction of the wall, same system as the ceiling, another thermal image, and then the output. Now, you'll see this is the same type of formula as before, but it has a different number here. The radiant ceiling, that number was 0.71. For a wall, it's 0.8. We actually get a little more convective output from a wall because it's a vertical surface. We do get some warm air rising from that, and that enhances the total heat output. So we have both radiant output and convective output. If we are working with 110 degree average water temperature in a 70 degree room, again, our difference would be 40 times 0.8. We're getting 32 BTUs per hour per square foot. So one of the things I really like about radiant ceilings and radiant walls, you don't necessarily have to cover the entire surface with tubing. Okay, you might find that you can get enough heat output, especially in a low energy building. You might only have to cover a certain amount of the wall or a certain amount of the ceiling with this type of construction. So that reduces the amount of materials. Now, having said that, the more surface area you do create, the lower the water temperature is going to be, and that is going to reflect on the performance of the heat pump. Here's a photo. We're looking up at the underside, and this is what's called a below floor tube and plate or underside tube and plate system. You can see the aluminum plates here that have been stapled up tight against the subfloor. You'll see a gap right in here. And then there's some more plates. And the reason there's a gap right here, this gap is directly under a kitchen island. And there's no point in adding heat to a floor that has cupboards or cabinets directly above it. In fact, if you store food in those cabinets, that heat is not good for the food. It'll cause premature spoilage of the food. So again, you can see the plates are stapled up nice and tight. I prefer to work with PEX, aluminum PEX tubing whenever we're working with aluminum plates. And that's not a code requirement. The reason I like the PEX aluminum PEX, the coefficient of expansion of the tube and the plate are almost the same. So you get very little differential movement between the tube and the plate as it heats and cools, and that minimizes any potential for little ticking sounds, expansion and contraction sounds, okay? Now, there is a graph over here and a formula. I won't spend a lot of time on it other than saying you could calculate your water temperature requirement. This is based on, again, 8-inch tube spacing. And it's a trade-off between the R value of the floor covering, and that would be what's on top of this subfloor. The subfloor is assumed to be a 3/4 inch oriented strand board or plywood, whatever you're going to put on top of that for a finished floor. The R value here gives you a value of K. You put that into the formula. And again, you have average water temperature minus room temperature. I would give you a suggestion, and that is don't put any finished flooring that has an R value of more than 1 over the top of that subfloor, okay? Now you're starting to push that water temperature up in that 115, 120 degree range. So this is not as good as a slab on grade or a radiant wall or a radiant ceiling. It's still workable within the temperature range of the heat pump, but it is starting to push that up. And what you don't see here that definitely is part of the system, there'll be a 6-inch fiberglass bat pressed up against these plates after everything's pressure tested. A couple other things, keep the drainage piping and your water piping below the insulation, especially traps. We don't want to put traps up under a heated floor and have insulation underneath them. What'll happen over time, if that fixture isn't used a lot, it'll actually dry up the trap and you'll get some sewer gas coming up through there. And the other thing, especially with cold water lines, you don't want the cold water lines running above that insulation because that will heat the cold water. And if you're looking for a cold glass of water and the heating system is on, obviously that isn't good. So small details like that are important. Now, this is something that you don't want to do with any heat source under any circumstances. You're looking at the underside of a floor. Here are the floor trusses instead of joists. And what somebody has done is clipped 1/2-inch PEX tubing to the side of that bottom cord on that truss. This is just electrical wire. This is not relevant to it. They expect this tubing to heat the top side of this floor. And that's just horrible heat transfer geometry. It's the reason we see this photograph. This is in the process of being torn out and redone, okay? So we have a term for this. We call this a thermally constipated floor heating system. And by thermally constipated, we mean that we can put high temperature water through that tube, but the BTUs just can't get out and get where they're supposed to be. So really bad idea. Okay, don't do that. And I'll show you one more. This looks a little neater. The installer here has taken 1/2-inch tubing and he's clipped it up into the bottom of the flange on I-joists. And it looks kind of neat the way he's done his loops here and so forth. But again, think about heat transfer. Think about warm water at 105 degrees trying to heat that floor up above there. It's just not going to work. There's not sufficient conduction away from that tube and across that floor. So again, I show you these. You won't see this in the European market, but you still will find people in North America that think there's something magic about plastic tubing that will allow you to do this and get away with it. Not going to happen, okay? So we're going to go to our second poll question. We've looked at several different types of heat emitters. Which low temperature heat emitters do you have experience with? And again, it's one of those check all that apply. So I'm going to let Carly run the poll. And while the poll's running, I'll just kind of go back and summarize. Again, You have a lot of options, and I should mention this, you don't have to necessarily pick one of these options and just use it throughout the entire house. You might choose to run floor heating in some areas, like in a basement, and maybe panel radiators or fan coils on the second floor. So you can mix a lot of these together. Just keep in mind that we don't want that water temperature under design load to go above 120 degrees. Okay, so it looks like the polls are running here. And it looks like a lot of people have had quite a range of experience from what I'm seeing here. Polls are closed. All right, so I'll just run this down. People that have had experience with slab on grade floor heating, 81% of you. Radiant ceiling heating, 25%. You work with radiant ceilings. Panel radiators, we're going to talk about those next, 56%. Low temperature fan coils, 54%. And then radiant floor slab on grade, 88%. So it looks like the folks that are on today have had quite a range of experience with these, and that's really good. You've got what I call a good heat emitter repertoire or portfolio. You have knowledge in several different types of heat emitters, and you also likely have knowledge on how you can combine multiple types together. All right, so let's go on. Now, panel radiators, one of my favorites. This panel radiator right here is about 2 feet high, 5 feet long. It's being supplied by a geothermal water-to-water heat pump. And it's operating under design load conditions at most 110 degree water. It's got a thermostatic valve up here. This allows each one of these heat emitters, these radiators, to be an independently controlled zone. So over here on the right, this is called a home run distribution system. It's a very simple idea. We're coming out of our buffer tank. We've got a variable speed circulator. We go to a manifold, and each radiator gets 1/2-inch PEX, or if you prefer, PEX aluminum, PEX tubing. So each radiator is on its own parallel circuit, all sourced off the same manifold station. And each radiator has a thermostatic valve, no batteries, no wires. That valve automatically responds to changes in room temperature, and it adjusts the flow rate going through the panel to maintain that room temperature. And it's a simple, very repeatable concept. I'm showing 6 radiators. It could be 8, it could be a dozen, it could be 4. Very scalable. These panel rads are available in different thicknesses and different heights, different lengths. And you can go to the manufacturers and get the data on performance. Real quick, these are examples of those small variable speed, high efficiency circulators. All the major circulator manufacturers today offer these in North America. Prices have come down a lot from when they first were introduced. These are the future of hydronic circulators. The standard circulators with the permanent split capacitor motors, you are going to see those phased out. I would say between 5 to 10 years from now, those will be gone. These will be the standard. Some of these circulators can tell you the flow rate going through them at any time. They can also tell you the wattage that the circulator is operating at. Taco just introduced this one, the 0018. That actually has Bluetooth connectivity. It can go right to your phone, and you can bring it up and see exactly what it's doing in terms of flow rate, wattage, and so forth. And it's the ideal, any of these circulators are ideal to tie in with that home run distribution system. This is just showing you a manifold station with 1/2-inch tubes going out to the different radiators, some air vents over here. Again, very, very repeatable, okay? Real quick, you can look at this more on the PDF file. It is important that when you size these radiators, you size them around low water temperatures. And there are correction factors over here based on the water temperature that you want to work with that adjust the output. Most of the manufacturers list the output at 180 degree average water temperature, well above where we want to be. But you'll see if you plot the data out here, here's a curve that basically gives you the output of a specific panel, a 2 foot by 4 foot panel with a 4-inch thickness. I will tell you right down here that with a supply water temperature of about 120 degrees, you can see that you're going to get about 27% of what you would at 180 degrees. Okay, so how's that going to affect the design? You're basically going to need larger panels. And the lower the water temperature that you design these around, the bigger the panel's got to be. But 120 degrees supply temperature at design load is very compatible with these panels. These do not have to have high temperature boiler water. You simply have larger panels. And the panel you're looking at here, I believe that is a 4x2, and it's about 4 inches thick. And you can see just 2 half-inch tubes right up through the floor, connect into the bottom. There's isolation valves down here if you ever have to remove this panel. And then up here in the corner is that non-electric thermostatic valve. That is the thermostat in that room that automatically adjusts the flow rate through that panel to maintain that room temperature. Panel rads have low thermal mass. There's really very little water in one of these panels. There might be a pint of water in a radiator this size, and that allows the panel to respond very quickly. So if you're bringing a room out of setback, this sequence of images over here on the right shows you this is when the water is first starting to go into that panel, and then this is 4 minutes later. And that panel is starting to approach a steady state condition. This graph just compares the thermal mass starting with a 4-inch thick concrete slab, obviously a lot of mass there, right down to what is an absolute state-of-the-art product that is a fan-assisted panel radiator. Has these very small little fans in there. These fans run on about 1.5 watts each, and that significantly improves that convective output from that panel. And you're going to see these develop more. There's one supplier that, there are not actually 2 suppliers in North America right now. I think you're going to see more offerings in the very near future on these. These are specifically designed around heat pumps, low water temperature heat sources. Okay. Dual fuel. You can tie a boiler in with the heat pump. There are several ways to do it. I'll just go to the next slide that kind of, well, let's talk about these. Where do you want dual fuel? Well, you might have an existing boiler, or you might want something that could operate in a power outage where you may not have a generator large enough to operate the heat pump. Okay. You might have off-peak rates where you're going to favor the heat pump as the heat source when you have low-cost electricity. And if you have high peak rates, go to some other type of heat source during those periods. You know, it could be gas, it could be propane, possibly even fuel oil. Okay. The AV unit, the Enertech heat pump, does have the logic to know when that auxiliary boiler is connected, and it can operate that boiler when necessary. Okay. So this shows a diverter valve. So the output that is coming basically from the heat pump right here, this would be the space heating heat output. That diverter valve, the diverter valve is for the auxiliary boiler. That determines whether the output from the auxiliary boiler goes to the space heating system or over here, over into that TurboMax indirect water heater. So this is providing a backup both to space heating and also to domestic hot water. There are different ways to connect the boiler in. Here's one way. This is with a set of closely spaced T's. It's connected downstream of the hydraulic separator. Again, to the left, you've got the variable speed pump and the zone valves, and these are just the returns. This shows it connected in parallel. This would be on the upstream side of the hydraulic separator. This has the advantage that, it allows whether the heat is coming from the heat pump or from the boiler, it all goes through the hydraulic separator, which, remember, that's also doing air separation at the top and dirt separation down at the bottom. When you connect that boiler up in either of these configurations, make sure you put a purge valve here so we can get the air dislodged out of that. And you do need a separate circulator to provide flow through the auxiliary boiler. And then finally, here's another connection. This is showing a buffer tank, a 3-pipe configuration. So again, you see whether the heat is coming from the boiler or from the heat pump, this is giving you that possibility for direct to load heat transfer. And the boiler in this case, as well as the heat pump, would be controlled based on the tank temperature. And then again, purge valves over here on the return side of these zones. So again, there's several ways to do it. These can all work. There's slight differences in them. No strong preference here. This shows, again, this is a parallel connection where we've got a heat pump over here. And again, it could be the air and water, it could be a geothermal water to water. We've got a check valve in here, so we don't want flow, both reverse thermosiphon. We want to eliminate that, as we talked about earlier. We also don't want flow that, let's say, this circulator is creating through the boiler. We want all that to go this way. We don't want it to go back through the heat pump. So we're putting a check valve in here and a purge valve. Same thing down here. So in general, anytime you have parallel circulators that can operate independently, we don't want flow reversal through the circulators that are off. Put a check valve in, okay? This is a ModCon boiler. This can go right down to low water temperatures, and there's nothing detrimental that happens to the boiler. It's got a stainless steel heat exchanger, okay? It's designed to operate at low water temperatures. But I want to caution you, if you've got an existing system that has a cast iron boiler, a steel fire tube boiler, or a copper tube boiler, those boilers are not designed to operate with sustained flue gas condensation. So if you're going to use that boiler and you're going to connect it to a low temperature distribution system, perhaps you're taking what was originally a high temperature system and you're modifying it into a low temperature system, like we're going to talk about next week. We've got to protect that boiler against flue gas condensation. There's a couple valves on the market. Basically, these are just high flow capacity thermostatic valves, and they can take this cool water coming back and they'll actually blend it with some of the hot water coming out of the boiler so that the return water typically stays above about 130 degrees Fahrenheit. And that's a serious issue. I've seen systems where this kind of detailing wasn't done, and you can destroy that boiler in a matter of months due to sustained flue gas condensation. You can also create rust right through the vent connector pipe. So it's a safety issue. I just want to bring it up in the case where you're retrofitting a system with what we call a conventional boiler. Chilled water cooling, you can do it with wall-mounted fan coils like this. Here's a 3-ton. This is a GeoComfort air handler. This is 3/4-inch pre-insulated PEX that's bringing the chilled water to the coil. Okay, so we've got a central duct system here that does single zone cooling in the building. I like the 3/4-inch pre-insulated PEX. It's fairly easy to run it through, and you don't worry about condensation because of having somebody not glue the joints and the insulation together. Again, I'm sure most of you recognize this is a high wall cassette. This is very common when you have a ductless mini split system. Basically, it's the same unit with a water coil in it instead of a refrigerant coil, and that can be used for heating or for cooling. So again, you have options. You can do single zone whole house air distribution, or you could do room by room or area by area distribution with either wall mounted or low wall mounted or high wall mounted fan coils. Now, I mentioned earlier, be very careful with chill water. If you've not done chill water cooling and you've done hydronic heating, you may have, I'm sure you put in systems where you don't worry about condensation on a copper piping in a heating system. If you take this copper piping and start running 45 or 50 degree water through it, literally within minutes, there's going to be water droplets on the bottom of that tube dripping on whatever is below it, okay? This is a product that we've used before, and this is it's a plastic clip. It's made by this company, Holdrite. It goes into some unistrut channel, and there are ribs in here that structurally support the pipe. But the nice thing is you can actually tuck the foam insulation in on both sides, and you don't see it here, but this should be caulked with silicone all the way around there. And the idea is that we're not allowing any ambient air to get contact with that piping. And if you keep the air away from the piping, you won't have the condensation. If you're doing zone valves, you definitely want to insulate the valve bodies, but not the actuators, especially if those actuators, if those zone valves are going to function in heating, you will, in the heating mode, that actuator has to dissipate some heat. And again, don't insulate the actuator. Now, there's a corroded volute on a circulator, literally 6 weeks of operation from a brand new product to that in 6 weeks. So I'm not sure what the coating was. That was not bare cast iron. It had some type of a paint or a coating on it, but it shows you how serious this issue of insulating chill water piping is. Grundfos does make a small circulator. They do have the option of an insulation shell. If you use that, make sure you not only put the shell together, but you caulk all the seams. Remember, the idea is to keep the ambient air away from anything that is being cooled down in the chill water system. And the insulation shell, you can see here, does not go up over the motor. Never insulate the motor can on a circulator. Here's a table if you're looking to insulate piping with standard elastomeric foam insulation. Depending on the fluid temperature and what the surrounding air conditions are, what are some minimum thicknesses of insulation, and it also depends on the pipe size. Okay, so again, chill water works great for cooling. Just make sure you do a good job with that pipe insulation. Okay, now I'm going to run real quickly, just maybe another 10 minutes. I'll run through a system here. I'll show you a real system that was put together actually 2 years ago that has a mixture of low temperature heat emitters. This is the house, is a brand new construction. It has about 3,300 square feet of space. Okay, it actually has both a air to water unit and a geothermal water to water unit in it. And it's got a combination of floor heating and panel racks. There's the photographs. You can see it's got a 7.8 kW PV system on it. It is net meter, so a lot of the electricity that is used to run the heat pump is already being produced by that PV system. It does have very good insulation. If you look at the R values here, 3,300 square feet of space at a design load of roughly 35,000 BTUs per hour. It's just over 10 BTUs per hour per square foot of floor area at design load. Okay, all electric. You probably say, well, what's that chimney? Well, it's a small wood stove. So if there's a long duration power outage, there is a small wood stove in the basement. So that's what the chimney is. Tubing layout plan for the basement here. See, all the circuits have been laid out, measured. The black dashes, these are control joint crossings. So there's a little sleeve over the tubing. All these circuits come back to a manifold down here in the mechanical room. There's a circuit in a breezeway here. You can see that's close tube spacing because there's a higher ratio there of wall area to floor area. It's a space that would lose heat faster. And then the garage is actually set up for floor heating as well. That all those circuits in the garage operate with an antifreeze solution through a heat exchanger. So the owner can just turn those circuits right off if they don't want to heat the garage, and nothing's going to freeze. Okay. Again, you can look at all these in more detail, and I would encourage you to do that in the PDF file. Just some photos of the installation. See, the basement walls are all insulated, and here's that 2-inch extruded polystyrene foam. This is a textbook example of tubing layout where the contractor's taken that drawing and they've actually spray painted where the returns are going to be. The yellow is where there could be some of future partitions. Those partitions are not in the initial construction, but they were identified on the plan. And so he spent some time with his rule plan and some spray paint. So when it's time to actually uncoil the pipe and fasten it down, it goes pretty fast. Temporary support for the manifold station here. Here he is fastening the tubing down. You see these are the sleeves where the control joint crossings are. Okay. And this is a simple system. It actually has a mixing valve because this system only needs, well, let's see, at 0 degrees outside, this system needs about 88 or 87 degree water. So we're actually blending the temperature down from the buffer tank. The buffer tank is being supplied by the heat pump, and because there's panel radiators operating at a slightly warmer temperature upstairs, we're actually blending that temperature down a little bit in the basement. Here's what 6-inch on center tubing looks like. That's the breezeway. You can see they've extended the bends out a little bit to take some of the stress off the piping. And when that's poured, that mesh and tubing is all going to be lifted up to about half the thickness. Okay. Won't spend a lot of time on this. This is a tube and plate underfloor system for a kitchen and dining room area. That layout takes a little bit more time. This is where the tubing is 8 inches on center, aluminum plates. Same thing in the bathroom here, okay? And then you'll see these orange rectangles. These are the panel rats. 2 of them in here, one in that bedroom, one there, and then the larger one in the master bedroom, okay? So again, it's a combination. So far, we've looked at 3 different heat emitters, slab on grade radiant, below floor tube and plate, and then these heat emitters, okay? Radiators. Here's the layout. You'll see some of the panel rads here have the thermostatic valves on them. There's a towel warmer in the master bathroom that has a thermostatic valve, but it's not on the towel warmer. It's actually under the floor with a capillary tube up to that device right there. So it does the same function, but it just isn't mounted directly on the on the towel warmer. Here are some examples of those panel radiators. You see 2-inch on center tubing right up through the floor, double isolation valve, and right up into the bottom of the panel. Okay. These over here, these panel rads and floor circuits are combined back to a common manifold. And the flow to that manifold is all controlled through a single zone valve by a thermostat. So that's a good example of mixed emitters. These are all going to get the same water temperature. All right, so they were sized with that in mind. And it shows you, again, a lot of flexibility here. You've got a thermostat controlling a zone valve for one area of the house. In the other areas, you've got 5 independently controlled zones using thermostatic valves. And that's all coming off of this little circulator down here. And that's the take-off circulator with the Bluetooth connection. And I can tell you, I monitored that. Oftentimes I find that running in the mid 20 watt range during a winter day to heat that entire distribution system. Here's the manifold. There's that zone valve this goes up to this collection of circuits here. There's another manifold that goes up to this collection of heat emitters over here. And you can see we've left some spares. I would suggest to you, leave at least one spare connection on each manifold. That way, if somebody does an addition on the house or they want to put another panel rad somewhere, very easy to tie that tubing right back in. You don't have to do, any extensive modification to the system. Just run the tubing through the framing and isolate the manifold temporarily, shut these valves off, and make your connections. There's that little pump that's running that, and there's an example on the phone. It shows you this pump happens to be in right now what's called a proportional differential pressure mode, but it shows you the operating point. It shows you right now it's operating at just under 16 watts at about 3,600 RPMs, and it's only sending out a little under 2 gallons. Now, I want to show you if we were operating this system at full output, that can provide about 43,000 BTUs per hour, and it will do that on 27 watts of pumping power. So last week we talked about distribution efficiency. It's just the rate of heat delivery divided by the necessary electrical wattage to run the distribution system. So we get this number, almost 1,600 BTUs per hour being delivered from the mechanical room to where it's needed per watt. And I just compared it to, let's say, a blower it could be a water to air heat pump, or it could be a furnace. Let's say we're delivering 48,000 BTUs per hour, and the blower motor needs 746 watts. We have a much lower distribution efficiency, okay? So that was actually based on some specs I took off of a unit, water to air heat pump with a 1 horsepower ECM blower in it. And just to again emphasize the advantage of dealing with a hydronic distribution system compared to a forced air system is much lower wattage for a given rate of heat delivery. And that fundamentally all goes back to what we talked about last week. That is the much higher heat capacity of water compared to air. Okay. Now that's it for today. We're going to take some questions in some time here. And again, next week, we're going to get into retrofitting. We feel that's going to be a strong market as state programs emphasize decarbonization and so forth. There's going to be market incentives to basically move existing hydronic systems over to heat pumps. The air to water unit is a good contender, but we want to show you specifically what are some techniques for modifying existing, what I'll call high temperature hydronic distribution systems to allow that heat pump to operate well. And Carly or Tim, do we have some questions that have come in?
We do. So the first question is, what is a lower outdoor temperature that it will produce hot water?
I'm sorry, what is the
lowest outdoor temperature that it will produce hot water?
Well, the Enertech heat pump's actually rated down to minus 13 degrees Fahrenheit. So we're still getting, water at a usable temperature with a low temperature hydronic distribution system. But I want to stress, at those conditions, our capacity and our COP are low. But if the person's just asking, is there a temperature at which this thing can't work anymore, it's actually rated to operate right down to minus 13. And Jim or Jeff, if you're on, I don't know if you want to comment on that at all. Okay.
Yeah, John, it's Jim. We're about at half capacity at minus 13. And then of course our COP, depending upon the water temperature we're delivering, in most cases we're still above, around 2 or a little bit above. So at minus 13, that's still pretty respectable. Those numbers, they increase significantly when we get up into the single digits above 0. So
yep. So it's definitely this unit is built for cold winter climate operation. What's another question, Carly?
Okay. How important is the pipe size from the outlet of the heat pump to the top of the buffer tank? Higher velocities would promote mixing?
Well, yeah. I believe the pipe size is 1 inch. Jim or Jeff, correct me if I'm wrong. I believe it's a 1 inch pipe for the space heating supply out of the indoor unit on the air to water.
It's going to depend on the length of the pipe coming from, the connection to the unit to the buffer tank. So if it's just through a wall, 1 inch is going to be fine. I saw some other questions that were asking about, how long can that length be? So it's a quick pressure drop calculation to see. In many cases, the buffer tanks that we're selling have 1.25 inch connection to them. So in many cases, 1.25 inch pipe is going to require less watts of the pump to move fluid. So upsizing is typically not a bad thing.
Yep, and the pump is built into the indoor unit. Basic hydronics is the farther you're going to go with a given flow rate, the larger the pipe size is. But as Jim was saying, short distances, which are typical, where you have the indoor unit and the buffer tank, let's say within a few feet of it, 1 inch pipe would be fine. If you're, for whatever reason, got to go a long distance, and I'll just throw out 50 feet. If the indoor unit and the buffer tank were separated by that amount of distance, I would recommend you go up a pipe size, which would take you up to 1.25 inches, simply to keep the head loss down and keep the flow rate up.
Okay, so next question, where is the best place to locate the ECM motor pumps serving the panel radiators?
Well, if you go back to the PDF and look at some of those slides, I come off the top of the buffer tank. We go through our air separating device because we want the air separator right where the hottest water is. And then I would say about a foot of piping downstream of the air separator, and then put that circulator right there. And the reason I say a foot of pipe, anytime you install a circulator, it's a good rule of thumb to have about 10 pipe diameters of straight pipe on the inlet of the circulator. So again, out of the buffer tank, through the air separator, nominal foot of pipe, put the circulator right there.
Okay, next question. Please talk about the temperature sensors locations in the tank when you have boiler and heat pumps.
Well, different tanks are going to have different locations. I'm showing a sensor well roughly at the midpoint of the tank. I think the GeoFlow tanks, it's just a little bit below the midpoint. Keep this in mind. You can have sensors at different heights in the tank and simply change set point temperatures corresponding to that. So for example, if I have a sensor in the midpoint of the tank and I want the tank to be, let's say at the midpoint about 100 degrees, let's say I'm going to turn off or turn on at some temperature. If I move that sensor up to the top of the tank, I'd probably change that set point. I'd probably bump it up by about 10 degrees because the stratification is going to keep the hotter water at the top of the tank. So theoretically, you could have sensors at different locations height-wise in the tank. Most of the commercial tanks, though, are going to have a sensor well or a connection for a sensor well at approximately the mid-height of the tank. And same idea with the boiler, okay? Some boiler configurations are going to go through the buffer tank. The ones that I showed you today actually do not go through the buffer tank. They go to the hydraulic separator. And so that would not necessarily have a sensor back in the buffer tank. If you're not using the boiler to heat the buffer tank, the best place for the sensor that controls the boiler modulation is on the outlet of the hydraulic separator. And the reason I say that is you're getting the true supply water temperature to the zones at that point. Keep in mind that as zones turn on and turn off, you're going to get different mixing conditions within the hydraulic separator, and that mixing is going to change that supply water temperature. For example, if you just turn on a zone that's been off for several hours, that's going to be relatively cool water coming back in. And by putting the sensor that's controlling the boiler on the outlet of the hydraulic separator, you're actually getting that net effect of all that mixing. So you're modulating your boiler based on what temperature is actually going to supply your zones.
Okay, and then do these air to water units qualify for all air source heat pump rebates?
Well, I would refer them back to specific rebate programs. I do know that the Advantage heat pump is certified for the Vermont program at this point, $1,000 per ton, and you can go right to Efficiency Vermont and look that up. I am not aware of other incentive programs right now for air to water. Hopefully we'll see that recognized in the near future, but I can't make a blank statement that says it qualifies for all the heat pump rebates. It would not qualify, for example, for a geothermal heat pump rebate. It's a different type of heat pump. So there is a website, DSIRE, I think it's .org, database of state incentives for renewable energy is what that stands for. And that is a database that you can go to, and they, I believe that's run through the Department of Energy. That database is kept up to date. So as different state rebate programs either come online or get modified, that's a good reference, or write to a specific utility or a specific state energy office to find out what would qualify.
Okay, and then the last question is, well, we've got some time for a couple ones. What are some of the factors to consider when coupling the domestic hot water with an Intertech unit?
Well, one of the things that's really nice about the Intertech unit, it has a domestic water mode. So there is a sensor that goes into that indirect tank that provides feedback to the heat pump, and the heat pump can start up and operate in, for example, a domestic water priority mode. So it could be, as an example, it could be operating in the summertime doing cooling. And if the controls are configured for domestic hot water priority, it will temporarily stop cooling, go into the heating mode, bring the indirect tank back up to a set point temperature, and then resume cooling. It's possible to do this with other heat pumps, but one of the things that the Intertech approach is providing is that's already been thought out, and the piping, the valving, and the control logic to do that is already built into that indoor unit.
Okay, and then two more questions. Is the Advantage unit applicable in the southern US where there's more of a need for cooling rather than heating?
I think it is. The cooling can be done with chilled water. You're bringing the advantage of a unit that can do domestic water heating as well as cooling, whereas a standard unit would not do that. Standard AC unit would not do that. And there is a market for comfort in the southern states. And I snicker a little bit about that because, I've had people say, well, nobody does radiant floor heating in Texas or Florida, Arizona. That's really not true. There's definitely a market down there for that. And, I won't try to say it's as big as the forced air market. It certainly isn't. But you get into the custom home market down in the southern states, those warm floors still feel really good, even in Florida in the wintertime. So yes, I would say this unit is certainly applicable in those southern states. Again, it's going to be chilled water cooling, but as we looked at today, we could do that with a central air handler. We could do it with area by area or room by room console type units. And we have the advantage that we can tie domestic water into that heat pump. The heat pump is providing domestic hot water, whereas a standard AC system would not be doing that for you.
John, I think it's really important to point out that many of the designs that we're seeing come through, the insulation values of houses all over the U.S., whether they be northern or they be southern, are becoming tremendous, where they've greatly reducing the loads for both heating and cooling of the house. And that's when actually the domestic hot water takes over as the largest load or the largest need for energy to operate the house. And that's really where this unit shines.
Excellent point. Very good point.
Okay, and the last question is, can you compare the SEER rating in cooling for the Advantage versus a high efficiency air-to-air heat pump?
Well, there actually is not a SEER rating, a seasonal energy efficiency ratio rating on an air-to-water heat pump. And the reason for that, it's going to depend on how that heat pump is applied. That heat pump operating at 45-degree chill water versus, let's say, 55-degree chill water is going to have a different energy efficiency ratio. So right now, there is no SEER rating on that. I don't know, Jim, if you want to toss that one in. I guess I look at it, the chill water, the energy efficiency ratio working with a chill water temperature of 45 to 55 degrees, it's probably a very small amount lower than an all air system would be, but you're also picking up versatility. The trade-off there is, again, with a hydronic system, you can craft that cooling system into zoning much easier than what you can do on the forced air side. And again, Jim, if you want to jump in with any comments, I'm they were asking about SEER rating on the Advantage versus some other systems.
Right, John. I know that like ASHRAE doesn't really have a testing standard right now for air-to-water heat pumps, but it's something that I do believe is in the works because, of course, they're gaining popularity. These types of questions are coming up. So there is a standard, I do believe, being developed at this time.
Okay.
And on that note, we can go ahead and wrap it up. I just want to remind everyone that we will be sending out an email with the presentation and the video from today. And then if you guys have any questions, feel free to submit them.
Yep, and download that PDF to take another look at some of those schematics that we kind of went through quickly today. And next week, retrofitting air to water into existing systems. See you then.
Thank you, everyone.